Yes, okay, thank you very much. Good afternoon, all of you. My name is Hassan Al-Zoubi. I'm from Al-Zaytuna University of Jordan. My field is differential geometry, which is pure mathematics, actually, pure mathematics. I finished all my studies from Greece, from Aristotle University of Thessaloniki, which means that I know Greek language. And I think Greece is my second country. I love Greek people. Also, Greek people are all my second family. The title of my paper is Quadric Surfaces in Terms of Coordinate Finite Type with respect to the second fundamental form. Okay. Introduction. So we have a surface Q in the Euclidean 3 space with referred to the system of coordinates V1, V2, and we denote by these symbols Gij, Bij, and Eij are the components of the first and second and third fundamental form of a surface. As we know, each surface in the Euclidean 3 space can be parameterized by a parametric representation, regular parametric representation. Each parametric representation, we know that has first fundamental form and second fundamental form and third. Also, it has a fourth fundamental form. So we will denote by I and the three I's of Q by the first, second, and third fundamental forms. Now, the first differential parameter of Beltrami with respect to the form in general now, we have a general form. This is the first differential, this is the first differential parameter of Beltrami. And we have gamma with respect to I is the partial derivative with respect to the parameter Vi, which means I is from 1 to 2, and Cij, this denotes the inverse tensor of the symbols, the Gij, Bij, and Dij for J equal I, or first fundamental form, or second or third fundamental form. The second differential parameter of Beltrami also defined as follows in this equation, where we have C represents the determinant of the Cij. For Cij, once is the first, the components of the first fundamental form, or the second or the third fundamental form. It's well-known relation for the position vector Z of a surface Q in the Euclidean 3 space. It was proved the following relation, this relation, where N is the unit normal vector field and K represents the Gauss curvature and H represents the mean curvature of the surface. Moreover, it was proved that a surface satisfying this condition with respect to the third fundamental form, here we know that delta is the second Laplace operators we mentioned before here. Satisfying this condition, for which all coordinates functions are eigenfunctions of delta with respect to the third fundamental form with the same eigenvalue, lambda is a part of a sphere or a minimal surface. Now I will give some fundamentals regarding the first and second and third fundamental forms of a surface. Now we can consider this parametric representation of a surface in the Euclidean 3 space. The metric I, or the first fundamental form of a Q, is defined as follows in this equation, where E is given, which is J11 is given by the dot product of this, where Rx is the partial derivative with respect to the parameter x, and Ry here is the derivative with respect to the partial derivative with respect to the parameter y. And as we know, this symbols denotes the Euclidean dot product. So we can find the first fundamental form from these equations, relations. And we have, for a sufficient differentiable function f in U, we have the following: the second Laplace operator with respect to the first fundamental form is given by this formula. Now, the metric, the second fundamental form of a Q, is given by this relation, where L, which is equal B11, which is defined as follows, where we have Rxx denote the second partial derivative with respect to x, and N, as I mentioned before, is the Gauss map. M is equal this, and N, from this dot product we can find it. The Laplacian delta with respect to the second fundamental form is given from this equation, and the third fundamental form is given by this relation, where E11 is equal Nx, where we have N is the Gauss map, and we have the partial derivative of Gauss map with respect to x, and here the Gauss map of N with respect to y, and we can find the components of the third fundamental form. I will go quickly now. So we have the second Laplace operator with respect to the third fundamental form is given by this relation. For any vector valued functions, we have the following relation. And now we have this definition: a surface Q is said to be of coordinate finite type with respect to the second fundamental form, or briefly of coordinate finite in this, if the position vector R of a Q satisfies a relation of this form of relation, where A is a square matrix of order 3. Now, our main result is the following theorem this is a mistake of quadric surfaces. In the things, the only ones that satisfy the above relation are the minimals and the spheres. Now, quadric surfaces of the first kind we have, which has this form, and a parametric representation can be found as follows here, and of the second kind in this form, and a parametric representation can be found in this relation. So we have to find the Laplace operator with respect to the second fundamental form. So we first must find the second fundamental form, that we can find it from here, the second fundamental form from here, where L equal this relation, and M and N, and we insert these relations in the Laplace operator, and finally we can find this relation, and we can find that delta with respect to the second fundamental form for the first component of the surface, which is equal this, and for the second components equal this, and the third component equal this relation. Now we apply all these for this relation. This relation we finally find after solving the systems. We can prove that spheres are the only quadric surfaces of the first kind with respect to the second fundamental form. Now, for the Laplace of the quadrices of the second kind, which I mentioned it here, the second kind, this kind. Yes, here. Okay, we find that delta R1 for the first component equals 0, for the second component equals 0, for the third component equal this, and we finally applying this, the relation delta 2r equal AR, we finally, after solving the above system, we can prove that there are no quadric surfaces of the second kind satisfying this relation. That's it, and thank you for your listening.